Hello everyone. Can you? Yeah. So welcome to the seminar. So we should start. So welcome to the seminar. Today we have Dr. Paolo Amore, who is a professor in the Faculty of Science of University of Colima, Mexico. He received his PhD in physics from the College of William and Mary, United States, followed by a postdoc at the University of Manchester. Paolo's work is mainly concentrated in the areas of mathematical physics and of computational physics. The Faculty of Science of the University of Colima has a successful undergraduate program in physics and mathematics. And Paolo is one of the persons who contributed founding these programs back there more than 2 decades ago. So welcome, Professor Paolo Amore.
Thank you for the invitation. It's a pleasure to be here. I'm gonna talk to you about some work that I've done in the past 2 years. It has been a lot of fun. It has a lot of phases. One is physics, but there are many more. So the outline, first I will talk about classical system of interacting particles, in particular mentioning the Thomson problem. I will come to that. Then I will switch to another kind of interesting system, which are related to packing and in certain geometries. Maybe I will talk about packing polygons, regular polygons in arbitrary domains of the plane and the spherical cups. And finally, I will look at a very special kind of configuration that exists in the regular polygons, which are called, which amounts to curved hexagonal path. And finally, I will draw some conclusion. So, I'm considering classical system of particles that interact with some potential. For example, they can interact with Coulomb potential, 1 over r, but it could be a more general potential. And I'm interested in finding a certain configuration that has the lowest energy possible. So it's a difficult problem if you think about it, because I have n particle. Each particle will have, we are in 3 dimensions, but for example, if I am in a sphere, I will have 2 degrees of freedom for each particle. And the number of configuration is known to be growing very fast as n grows. Studies on the so-called Thomson problem. Thomson problem is a name that people give to the model of electron and a sphere, and it reminds the original Planck-Paldin model of Thomson, which was not correct physically. But this problem is very interesting because there are physical systems that organize in some way, but also computationally is a very challenging problem. And the challenge is manifested by this formula. This formula was first estimated by Herbert and Oakley, which in 1997 studied the problem, made some simulation, and look, they found out that the number of local minima is growing exponentially with n. And they estimated this formula, which has not to be taken as a very precise formula. It just gives you an idea of how fast it is growing. Later on, in 2013, Kalev and collaborator made a more deep study of these and other potential, and they also confirmed exponential growth. But the point is that if you consider just 100 points on the sphere, you have about of the order 50 local minima. But if you go to 1000, you have 10 to the 21 estimated local minima. So it's a huge number, which tells you that even computationally, it's very difficult to find the global minimum of the problem. Finding the global minimum of the problem of this system for large number of particles is really a challenging problem. There are solutions that are known exactly, but it's for very low N, for example, it is known that the tetrahedron, the octahedron, the icosahedron are solution. As you go to very large N, you should approach the continuum. The continuum is this N in the energy is just this N squared over 2. It would be the energy of a conducting sphere. And then there is a correction, which also is subdominant to the rest of the dominant term. And this is an example of configuration for 112 points on the sphere. And there is one tool that we can use to visualize this configuration, which is Voronoi diagrams. So the main point here are that finding a global minimum is really challenging. There are we are in a 2n dimensional space, so there are of the order of 2n degrees of freedom. One cannot know when it does the calculation that he landed in a global minimum. This is a challenging problem. You don't know. You can check that it's a minimum, but how do you check that it's a global minimum? If you find something better, you actually discover that it was not a global minimum. You need to use efficient algorithms for the search of the global minimum. This normally amounts to use basic copy, and the time you have to dispose is large because these are really extensive calculations. So one of the tools that one can use to visualize this configuration is using Voronoi diagrams. Voronoi diagrams are a tool, very simple to explain. So if I look at the points on the sphere, I can imagine to partition the sphere into region of points most close to a given point. So you see that this point, this cell here or light blue corresponds to this point here that is has 5 edges coming out. And it should be not a surprise that the configuration like this emerged, because it is well known that you cannot tile a sphere with pure hexagons, right? So Euler's theorem tells you that the number of vertices minus the number of edges plus the number of faces for the sphere should be 2, which can be rephrased in this form, where S is now the number of sides of each cell. And so, for example, in this case, it will be 5. In the case of dark blue, is 6. And NS is the number of cells with SI. So the Euler theorem rephrased in this way tells us that if I count the number of pentagons, it should be 12. Okay, and the number of hexagons are not changing the balance, so I can have, of course, the total number of cells has to be equal to n, but the total number of particles, but I have this requirement that the least I can have is 12 pentagons. Okay. Okay. So, for example, this is a more complicated configuration found numerically for 2,000 points of the sphere. You run your algorithm many times, and you see where it lands. You try to discard the configuration that are of higher energy, and eventually you land in some evenly. So the main information that we get from this diagram is that as the system grows, also the kind of what one calls topological defects changes. Before you had isolated pentagons, and now you have something weirder, because you also have pentagons, but accompanied by heptagons. These purple cells are heptagons. So again, if you count all the number of topological defects with this recipe, that pentagons have a negative, have a positive 1 topological charge, heptagons has a negative 1 topological charge, the sum of all charges, topological charges, has to be 12. Okay, so it may be very complicated, but the Euler's theorem forces you to learn all that. Here you see a kind of very nice effect, which is a rosette. It's called the rosette, which is a pentagon surrounded by heptagon surrounded by pentagon. It counts like -1 because there are 6 pentagons and 5 heptagons, okay? So it's kind of complicated. So Euler's theorem is a theorem, so it tells you what must happen. However, it doesn't tell you how it can happen. So it doesn't tell you that you will have only 12 pentagons. It tells you a balance, and this balance can change with the density. In some cases, you will find that solutions with very high symmetry are really appearing and are favorable. Actually, the last example I will give you is all about this. And on the other hand, you also know that in the limit of very large n, you should approach the continuum limit. Okay? So another kind of problems with a different geometry would be the Thomson problem now restricted to a flat disk. Imagine that you have a flat disk. And in this case, in the continuum, you don't have a uniform charge distribution. The charge distribution is like this. It has a singularity, but integrable singularity at the border. And the energy for in this continuum limit scales like pi over 4 n squared. The number of configuration also in this case is exponentially large. The difference with the previous example that in the previous example you don't have a border, and now there is a border. So it's challenging. The border makes the problem also challenging because you can imagine that the real ground state, the real global minimum of the problem prefers a certain number of border charges. And with some qualitative estimate, you can find out that the number of border charges scales like n to the 2/3. With this in mind, with the student in mind, we have devised an algorithm which has two basic ingredients. One, to constrain the program to build and work with solution with a definite number of border charges. And the second is trying to look at solution with a large number of charges, total number of charges, but with a divide and conquer algorithm, which means subdivide the problem in freeze many of the degrees of freedom, work with a lower number of degrees of freedom, and try to little by little find the solution. This is the largest solution we found. This is a very large number of, we cannot claim it's a global minimum. It's not, surely not. Here, the most important thing is to notice the kind of very complicated pattern of topological defects that appear in the system, and particularly close to the border. The system is non-homogeneous, even in the continuum, which means that the Born cells close to the border are much smaller, much thinner than the Born cells inside the border, or far from the border.
Is this two-dimensional or are
this is two-dimensional?
Two-dimensional, not sphere.
Not the sphere. This is two-dimensional. In the sphere, it will be much more uniform. So now we go to a rather different problem, which is circle pathing. So instead of considering an interaction between distant points, now consider an interaction between rigid objects. Okay? This algorithm, well, the problem here is also different in the sense that you want to maximize the pathing fraction, which is the fraction between the volume or the surface occupied by the disk and the total volume of surface available. Okay, this is called the pathing fraction. And if you consider, for example, a disk in a square, what you will do, you will try to arrange your disk with the maximum possible size that can all fit in the square in a way that they maximize this pathing fraction. I started to work on this problem after reading this paper. This is a paper from 1997 in which it described an algorithm for solving this problem. It's a heuristic algorithm, and it works it works rather well for the square, but we have to take in consideration some points in this problem. First, it is a constraint optimization problem, which means it's not just a problem of optimizing. I also have to fulfill some constraints, which makes the problem a little bit hard. The number of possible packings also is very large, it's huge, so that makes the problem so difficult. Another difficulty is that there are configurations that can vary by tiny amounts of packing fraction, and if you look for the global maximum, that's also challenging. Proof of optimality, formal proof of optimalities for different geometry are very few, and typically for the square are for n smaller than 32. And there are upper bounds because there is this theorem, Q's theorem, which is the two-dimensional equivalent of Kepler's conjecture that tells you that the maximum the packing fraction in the plane is p over square root of 4. Okay, so how does the algorithm work? The algorithm of Normela and Amsterdam. It works this way. You first put n points randomly on a square, and you parameterize the points like this. So this parameterization is very clever because all of a sudden it transforms your problem from constraint optimization to unconstrained optimization, because automatically the Cartesian coordinate expressed this way fit in the square. So that's good. Then you regard the points as charges, okay? But a weird kind of charges, because they will change the interaction during the algorithm. You start with a parameter S, which is rather small, which means long-range interaction, that helps you at the first stages of the algorithm to put order in your things on a large scale. And then you start increasing the value of S. This parameter lambda is a parameter which gives you at each step of the algorithm the minimal square distance between points. So essentially, you end up at the end of the algorithm with a value of S which is huge, which mimics a contact interaction. Okay, really an explosive interaction. The disk at the point can only touch, but they cannot overlap. Okay, and you check the packing fraction. If you improve the value of the packing fraction, you get this solution. Otherwise, you draw. Okay, so this is one example. 7 disks inside the square. This is nice configuration. It has some symmetry, not so high symmetry, but it has. Okay. Now, the question is, can I generalize this approach to different geometries? For example, different containers, different three-dimensional space, different curves. So there are some technical details. For example, the algorithm on Normela Hostegar has a feature that doesn't work with a fixed container, because it works with this red container, which is the container of the center of the disk or the charges. The blue container is the container you find at the end of the algorithm, which is the real physical container. So the size of the disk is not determined a priori. It's determined when you calculate the minimal distance between any 2 points. Then you know what the size of the disk is. And in order for the algorithm to work, you have to have a property, fundamental property. The blue and the red containers have to be related by a scale transformation. If they are not, you cannot you cannot work with this algorithm. So let's see an example. This is an example. Imagine that you have an elliptical container, and then you want to scale this down. Oops. Okay. When you scale, they don't overlap. So the electrical container, for example, wouldn't be good for the algorithm. It cannot do it. But there are problems that can be done with this original algorithm. For example, regular polygons. Actually, the circle and the square are special case, right? So if I look at the packing in a regular polygon, I can adapt the algorithm. The algorithm works. I did some calculation. I had a lot of fun. The main point here is that we can work exactly with the same kind of algorithm and try to find the best configuration. Also, in this case, as in the Thomson problem, you have to comply with Euler's theorem. Just the difference is that because you are in a plane, the sum of the topological charges amounts to 6 instead of 12. Okay. These are examples of configuration. This is a configuration of 12 disks inside a hexagon, and this is the corresponding Born diagram. Okay. These are other configurations. For example, this is all for the dodecagon. So we have 2, 3, 4, 5. There are some nice configurations. Actually, one point that is important to make is that there are special also domains like the hexagon and the equilateral triangle that have some magic numbers, which are triangular number, hexagonal number, and which solution with very high symmetry of color, which are solution with hexagonal symmetry. So let's see if we can look at some of the solutions. This, you see this. You have perfect hexagonal packing in equilateral triangle with these specific triangular numbers, and also you have, it's not a big surprise, you have perfect hexagonal packing in the hexagon at this special number, hexagonal numbers. These are the configuration, these are the Born diagrams. Okay, so now, can you work with more general domains? With some students of mine, we had an idea on how to extend this algorithm. It's very simple, the idea, and the inspiration comes from classical electrostatics. In electrostatics, when you study, you can find that the image charges are a powerful tool that can simplify a problem that at first looks difficult to convert it in a much simpler problem. So, what I'm gonna tell you is not, you don't have to take it literally. These are not image charges as in electrodynamics, but the idea, the philosophy, the inspiration is similar. So how does it work? It works in this way. Let me show you the diagram. So this is an arbitrary domain in which I first throw 5 points in the domain. These points, eventually, I will try to maximize the distance and see what packing they give. But now I have a fixed container. This one is a fixed container. And if I just apply the algorithm as I explained you before, the points will eventually flow to the border, and I would have to draw the outer border, and it wouldn't be related by scalar transformation. I wouldn't be able to perform the algorithm. But here what I do is invent other degrees of freedom, which I call image charges, which are on a line that connects the border, and it goes to the border normally, and they extend by a similar amount on the other side. So this is not a physical point. This is a point that interacts only with this point here, and when this point here gets too close to the border, it repels it. Okay, so it makes essentially makes these charges, this stick inside the domain without any problem. So this is the final evolution of the algorithm after I do this recipe. As you can see, now I have no problem. A point doesn't need to have mono single image charges. Like in this case, you see you have two because it's equidistant from the border in two directions. Okay, you can even have more if needed. So this is the idea, and this idea allows to extend this treating of packing to more complex geometry. For example, we have looked at crosses, cardioids, cylinders, spherical cups. So, for example, these are particular configuration in the cross. for very special value of this parameter A. This parameter A is the ratio between the length of the arm and the width of the arm. Okay, and if I keep varying and I look at the density will change. But these are maxima. Okay, these are maxima of the packing fraction. And the nice thing to observe, especially in these two cases, is that they correspond to highly symmetrical solutions. Okay, eventually symmetry pops out of the problem because symmetry allows you, in certain cases, to maximize the density. Okay, so these are the Voronoi diagrams, same thing as before. And now another example of application into spherical cup. The spherical cup is a portion of the sphere, so it is interesting because it's an intermediate case between the two cases we considered before, not for packing, but for the Thomson problem. It goes, in one limit, it goes to the flat disk. In the other limit, it goes to the whole sphere. By the way, the whole sphere was studied in packing in 1930-something by a botanist, Tames, who was interested in the distribution of spores, okay? Of spores on pollen grains. So it has some inspiration from botany, but it also, you can look at the biological system with this kind of problematic. You can look actually to physics in experimental physics. I found out the only reference I found out that had some kind of calculation or pattern calculation for in physics or in general was a paper on the 90s in concerning the building of a solar and spherical detector. Okay, they did some simulation. I think they consider up to 40 something disks. They didn't do an algorithmic search very extensive, but they found some kind of calculation. And also in architecture, because domes, geodesic domes, are an example of this. So this is an example. The eyes of an insect have something to do with packing on a spherical cup. And this is another example. This is the Montreal biosphere by Mr. Fuller. And I just want to show you this special configuration. This is a special configuration that I found for theta max is the width or angular width of the cup, which in this case is p/6. And at this number of particles, 157, you discover that there is a highly symmetrical configuration emerged. So now I want to come to the most aesthetically pleasing part of the talk, which is about purpose angular packing. So a long time ago, in 1997, Brown and Lubachevsky discovered that in the circle, you can have very nice configuration, we call them purpose angular packing, that are a modification of the perfect hexagonal packing in the hexagon. So for the same number of particles, in the hexagon. In the circle, you find that at these magic numbers, you have something that is a modification of the hexagonal packing, and is maximal up to this number of disks. So this is the best solution up to 91 disks in the circle. So with two of my students, we first we discovered by the algorithm, numerical algorithm, that in regular polygons with a number of sides that is multiple of 6, you would have at this special number, you would have highly symmetrical configuration. Very nice. And at first we wanted to try to find them numerically, but then we figured out a way to find them not analytically, deterministically. So what do I mean by this? So in the algorithm that we devised, and it works pretty well, it works like this. First of all, you have to realize that because of the symmetry, you don't work with the whole domain. You can work with 1/6 of the domain. That has the same symmetry of the S. And then the second ingredient is that in hexagonal packing, the border of the domain is fully packed. So you start from this vertex, and you have to end up eventually in this vertex. So that allows you to determine exactly the location of the disk on the border. Once you have that, you have still to find out how do they distribute internally. So, yes, it's not needed. You have to find out how to distribute internally. So you have to find a way to put this on this region here. So, I don't want to show many numbers. One point that I want to make is that there are really a lot of configuration that are degenerate. So for a given magic number, there is a factorial number of configuration. This K is the number of shells that I have in the problem. I want to skip the technical details, but the point, how do I construct this configuration? So first I have this layer here, which is calculated, and then I have to connect this point here with this point here. I can do it in many ways, but we have a conjecture in our work, which is not mathematically proven, is that the conjecture states that if I connect two disks on the border, and I call this angle phi, phi1, phi2, phi3, phi, and then I do the same between this point, and I call this angle psi, the two angles are related, and the angle psi are a permutation related to a permutation on the angle phi. So when I want to build a configuration, I have to choose one of these permutations, build this skeleton, and then what follows is filling the gaps. So I have a simulation, I want to skip this, but I have a simulation that will show. So I have to fill in the gaps like with the compass, okay? Unfortunately, the shading is not appearing very well, but once you fix this disk here, you can find the intersection and fill in the new layers until everything is set. Okay, so the algorithm works like this. I have a simulation. Unfortunately, in Adobe, I couldn't run it, so we will have to run it externally. Yeah, I have two simulations. It's in Paolo. First, the deterministic algorithm. Okay, so here you see how it works. Okay, this is how the algorithm works. Now we'll see a number of configurations in the dodecagon with 8. These are all configurations with the same packing function. Okay, they change. What changes is because of this permutation of channels. Of this, there are a large amount of configurations. We can go back to the slides. These configurations for the dodecagon are slightly more advantageous than for the circle, around 120 something. There is still a maximal density configuration with this symmetry, but in general they are lost for a very large n. So the symmetry eventually is okay. The symmetry eventually is going to be lost. Okay. Another curiosity, it was very, very curious for me, is that apparently there are some special configuration which shouldn't have symmetry and they have. So this is for 37 disks on a non-agon, and this is 37 disks on a regular polygon with 27 sides. The domain doesn't have the symmetry of the hexagon, and yet the configuration inside has the symmetry of the hexagon. These are the only two we found, but it's so strange. These are other configurations that emerge with symmetry. They have a completely hexagonal packing in the inside, and then a partially filled border on the outside. And these configurations are also configuration of maximal base. Okay. This is another way of application of this will be, for example, for this large number of particles, 1,657, this, I wouldn't dare to think that this can be a good hacking Actually, it's not. But what I can do is, instead of feeding my numerical algorithm with a random configuration, I can start with a very well organized configuration and then perturb it with a single perturbation. I get to a much larger density. So it can be useful to have symmetry, even when I know that symmetry is not the solution to my problem. Okay. For this kind of number of particles, there are 8 million of curved hexagonal packing available. Okay. Okay. So this is also intriguing because this is the Voronoi diagram of the symmetrical configuration. It has square, pentagons, and hexagon. And this is the other configuration found by optimization, which is interesting because, as you see, it appears that topological charge is almost always spread to the border. The inside is almost completely hexagonal. Okay. Okay, now the conclusion. The conclusion is that finding a ground state of one of these systems is really challenging. It is also interesting. It's a NP-hard problem. It has interest in physics, probably, but also in other areas like mathematics, computer science, and so on. The curvature and the border are sources of geometrical frustration. Doesn't let me do what I would like to do in an infinite space. For example, in an infinite plane, I know that hexagonal packing would be the way to do it. But as soon as I have a border, as soon as I have curvature, I cannot do it anymore. And I have some long-term goals, like, for example, attack configuration of very large N, study different geometries, but also to explore the energy landscape of this problem. For example, right now, we are looking at the energy landscape of the Thomson problem. And one thing that is really interesting is the number, not of me, but of stationary point, is exploding much more than the number of local minimum. It is huge. So it's really a complicated problem. So with this, I think I can stop.
So now we are open for questions. Yes.
Okay, I have a question. It's regarding like one of the slides. It's like the curved sectional packing, like one of the early slides for that.
Yeah, let me.
I just wanted a clarification on the
Which slide?
before earlier. Oh, this one.
Yeah.
I was wondering like what the values along this.
Okay. Yeah, density here is the packing fraction. So packing fraction means you measure the area of each. These are all the very same distance, same size. Okay, you measure the area of one, you multiply by n. This will give you the area covered by this, and then you divide it by the area of the container.
I was more asking about like value.
Okay, the value below this is the notation of Bernoulli-Lobachevsky. It has to be related to the diameter of the container, in this case the circle, and the diameter of the disk. I'm not sure about that. This picture actually is taken from this paper.
Thank
Okay.
you.
One of the biological examples you mentioned was the shapes you get in virus capsules, these very regular geometric shapes. In there, you have more than one type of protein forming this. So in your model, it would be like spheres of two different sizes. Have you tried to model these? You have more than one type of circle.
I'm a novice in this kind of problem, so I have interest in trying to look at polydispersed packing. Trying to look at building blocks of different sizes. That's certainly interesting problem. This problem is quite challenging already.
Yeah, you're definitely certain problems.
Yeah, but this is definitely something that I would like to do as well.
It's very cool. I just wondering that if we're able to get the dynamic information of all of the for one simple case like this, another one you could.
By dynamic information, what do you mean?
Like one configuration that you change your boundary, like
Okay.
twist a little bit, or you.
Okay, we did some kind of simulation. For example, in at one point going from the circle to the cardioid gradually, not continuously, because you have a parameter and you modify it little by little until you land on the cardioid. And the reason why I wanted to look at the cardioid is the cardioid has a border singularity. So it is kind of a strong.
Because there are a lot of configurations would be follow a minimum energy pathway or kinetic.
Look, what I can tell you, for example, in the case of the spherical cap, as you start with in the spherical cap problem, what you do is take a cap of infinitesimal size, but on a huge sphere, so that the area is equal to pi. Okay, and then you start enlarging the angular width of the spherical cap. So, for example, for one of these magic numbers, for example, 91, you will start with a configuration like this. Okay, and then you start enlarging the cap. At one point, it disappears. It's not that it disappears. It's not the best one anymore. And the reason is very simple to understand. Curvature unpacking requires the border to be fully packed. As you add curvature, you get to a point in which you have enough space inside that you can take a and that makes curvature unpacking to disappear when you add curvature at some point.
Just about the biological and botanical examples, have you calculated to see how energy efficient or packing efficient what is naturally occurring is? Like, I would assume that it's.
I've been focused more on the computational side of the problem. But actually, she knows a lot, much more than me. She works in application like biophysics. I'm not a biophysicist, but yes, I find all this area very intriguing and very interesting.
I'm curious on the biological application. You could have a lot like the filament-based virus packing, like cells when you have division from the embryo, how they're dividing and getting the pattern.
Another kind of application that I didn't mention, for example, in applied mathematics, there is the associated problem that you want to discretize a surface, for example, and this gives you a way to discretize, right? Pick points on a surface. So you can look at it from different sides and find something.
It is interesting you borrowed the idea from the well-known image problem and applied here. Now again, in the image problem, we have a conductor. Now, in this case, you're assuming the region surrounding your shape is almost like a conductor.
Yeah, the image.
I know you said
the inspiration is it's just an inspiration. You don't have to take it literally, but it's actually the image problem doesn't work with borders.
Yeah. So, what I noticed in that picture you showed, for some disks, you put in 2 image disks. But for some of them, although they touch the border in 2 places, you put only 1.
Yeah, that's let me look for the.
Oh, yeah.
There are 2 images. This is the first stage. When you are at the first stage, points are disordered. So the size of the disk is dictated by the smallest distance between any 2 pair of disks at the first stage. Okay. In this case, what normally happens is that each disk has one single image disk associated. When you apply the algorithm, many repetitions, you go to this final stage in which the points landed into a final configuration. If the final configuration is such that, for example, in this case, this point is equidistant from the border, it will have two image distance. But it depends. You don't know a priori. You know it at the end.
The image of particles more like steric repulsion, like exploding.
No, they can even overlap. The image particles don't see each other.
But image and the real.
Oh, image and real, they follow the same interaction as.
The goal is not to remove the boundary, but it's to.
Yes, to force the particle inside the particle.
Inside.
Yeah, that's the goal. Yeah.
So that one, on the bottom left, then, there is an, the one inside,
This one? This one.
Yes, so that one, to my eye, appears to touch the border in two places, but probably it doesn't.
It doesn't touch the border actually. If you come here, you will see that there is small gap and there is small gap.
That's what.
It's a tiny amount, but for the computer is enough to discard.
Sure.
So in the hydrodynamic code we use my galaxy formation simulations for each particle that moves along, there's a Voronoi tessellation that's
Okay.
used to sort of create a grid around that particle, which makes me wonder, and I'm sure since you said, you just started on this or you're novice, you said, you thought any about like the three-dimensional problem.
Three-dimensional, you mean in
Yeah, like-
volume.
Yeah, well,
It's much more difficult. I haven't thought about that. One of the things that I'm right now interested in is I was asking as you before is how, for example, if we look at the Thomson problem, we know that in the large n limit you go to the continuum. However, to me, it's not clear how the topological defects go in this limit. There is a continuum theory. She is an expert on this. I don't know anything about that. So my current curiosity, I found out that there are bounds on certain quantities, mathematical bounds. And with a colleague of mine, we have been able to find the proof, alternative proof of this bound, and an alternative bound as well. And I want to apply these bounds to look at the distributional defects in the large n limit to see if this bound can tell us pinpoint some feature of this system for n very large. So this instead of looking at all the points on the sphere, I would select only the defects, and I will see if the defect follows some kind of pattern. That's my present curiosity.
So I have one question. You mentioned about the magic numbers and the relationship with the
So
numbers.
magic is not to be taken later.
Yeah. So this the 91 inside this circle and all the. So depending on the symmetry of the boundary where you fit this thing, is there a relationship with some abstract mathematics number theory with certain kind of shape with the number that is inside?
I'm not sure. Graham was a mathematician. This Graham and Lubachevsky. Lubachevsky was a computational physics, but Graham was a mathematician. There are a lot of people in mathematics which have worked on formal proof for certain domains. These proofs are very difficult to. Actually, if you think about it, Kepler's conjecture has lived almost 400 years before being proved. So it means something. It's very simple to understand, yet proving is another matter, right? So I'm not really sure about deeper insight in this problem.
Gotcha. All right. So if there is no other question, do you have a question? Oh, no. Okay. Sorry. So let's thank our speakers. Next week,
Who's the
oh yeah,
speaker?
next week's Francisco, it's an alum here. Francisco
Yeah.
Mercado was a former student here. It's gonna talk about
That's
this.
2017,
Yeah,
if I'm
talk
not
about his
mistaken.
Galaxy formation.
Justin, okay, I will, I didn't know. Well,